Hi everyone, I hope you are all well. Welcome to another maths lesson. So today I'm going to start off by looking at my checklist. Of course, I've been talking about this checklist constantly the last few weeks and months, and I really would like you guys to continue updating your checklists as I am doing after every single lesson I cover with you guys. So as you can see here, don't focus on the writing on the side and at the top. Just focus on the topics which have been highlighted in either green or yellow. Now, of course, the topics which we haven't covered yet, I've just left them completely. So like gradients and areas under a graph, we will do that after the half-term break, hopefully. In terms of the topics which are in green, these are the topics which I'm hoping you guys are fluent with as well. And the topics which are in yellow, well, we will revisit those hopefully in the coming weeks and months. As you can see here, I have, you can see that we have completed the probability topic. I have highlighted conditional probability in yellow because there are some people from our class who are yet to submit work. Hopefully, if you guys catch up, then I'll be able to tick that off, highlight it in green, and we'll be able to, I guess, focus more on other topics. I've also made a note of algebraic probability here because I noticed quite a few of you found those questions quite difficult. So hopefully we will revisit some of those questions over the coming weeks and months as well. I would really like you guys to continue recapping previous topics. We have covered so many topics just in year 11, and that includes all the recap work we have done since the start of this year. So please make sure you're constantly looking over your book, looking at your notes, looking at YouTube videos, any websites which you use, and you are regularly updating your checklist. I would really like you guys to be fluent with all of these green topics because chances are I won't be revisiting a lot of them. We just simply don't have enough time to test you on all of these topics. Before I start with today's lesson, I want to bring your attention to a video I uploaded to my YouTube channel last week. On Thursday, we did an LBQ quiz which consisted of 5 questions. I uploaded the solutions onto my YouTube account, and this is the title of the video. So, and of course the link is here as well. So please make sure you go on that video if you haven't done so already. It is good that we are challenging ourselves doing these really difficult questions, but if you're not looking at the solutions, if you're not checking to see if your answers are correct, checking to see where you can make improvements upon, then there is no point of doing these hard questions. So please make sure you have a look at that video. Moving on to today's lesson, the title is Compound Growth and Decay. And on the screen, you can see the PPE Paper 2, question 10, which you guys did a few months ago. Now, the reason why I've showed this question, displayed it on the screen for you guys, is because it is a compound growth question, and hopefully by the end of today's lesson, we will be able to revisit this question and use the things which we learned during the lesson to answer this exam question. So firstly, as you can see at the top of this exam question, they've written a number in standard form. Now, we haven't really done much work with standard form. You should have learned about it in either year 9 or year 8. And so I think it's useful to talk about it for a few minutes and do a few practice questions as well as a starter to today's lesson. So standard form is a way of writing really large or really small numbers. You may have seen values in standard form in your science lessons. I know that standard form numbers are used to represent things like distances between planets. So that's something you might see in science. Of course, the size of bacteria, if it's what's the word I'm looking for? If the bacteria is microscopic, then chances are its size would be measured using a value which is in standard form. So there are a few key rules. This value here must be between 1 and 10. That's a big misconception where people will think values such as this one are in standard form. No, this is not standard form. It would have to be 1.2 multiplied by 10 to the power of 6. So we talked about the first rule. Standard form is always 10 to the power of something. Yeah, so you always have to multiply the a value with 10 to the power of something. N must be a whole number. This is the number of places the decimal point moves. So here we have an example. As you can see, the n is a whole number. Of course, the link at the bottom is a link to Maths Made Easy, where there is some further practice and further, I guess, explanations of standard form. Here we have 2 practice exam questions which I would like you guys to answer. So please pause this video and have a go at answering these questions. Once again, if you would like to do further practice on standard form, then maybe click on the link below, try answering some different questions or look at some different examples. I'm going to now go through the answer to question 1. So Jake noted that speed of light is this, speed of sound is this, and so we're going to use this information probably. Notice how I'm underlining the key information. Oops. Yeah, notice how I'm underlining the key information, and it's just like why I say constantly, make sure you're highlighting the key information, and that will help you answer the question. So it says, using Jake's figures, how many times faster is light than speed? So how many times faster is light than speed? So we need to divide 1.1 multiplied by 10 to the power of 9, 1.2 multiplied by 10 to 3. Okay, now I can see why they've written this. So we want to get ourselves in a situation where we have 11 divided by 12. So let's write 11 here multiplied by 10 to the 8 over 12 multiplied by 10 to the 2. So 11 over 12 is 0.916 recurring, and 10 over 8 divided by 10 to the 2 is 10 to the 6. It says write your answer in standard form, so now we need to write this value in standard form. So we're going to multiply this decimal by 10, 9.16, and so we need to divide by 10. We need to do 10 to the 6 divided by 10, so these two values are equivalent. And so we have our value. Of course, the units are kilometers per hour. Question 2, find the value of k. So we have our equation here, and it looks like we have to substitute these values into that equation. So AB is going to be 2 times 6 multiplied by 10 to the 4 multiplied by 10 to the 6. So it's going to be 10 to the 10 divided by B take away C. So this is 6 with 6 zeros, so 6 million. And here we have, going to try to align it. So 1 0 0 0 0. So B take away C is 5.9 million. One. I think that's it. Sorry. Yes, 5.9 million. So in standard form, it would be 5.9 multiplied by 10 to the 6. But here it says 12 divided by 59. So we're going to try to get ourselves in a situation where we have 12 divided by 59. So I'm going to write 12 multiplied by 10 to the 10. And I'll change this to 59. So we've made this, the A value 10 times larger. So the power of 10 has to be 10 times smaller. Yes. 12 over 59 is 0.20. 10 to the 10 divided by 10 to the 5 is 10 to the 5. Is in standard form? No. So multiply the A value by 10 and divide the powers of 10 by 10. Yes. So we have 2.0 multiplied by 10 to the 4. Now notice here it says correct to two significant figures. So we have to write 2.0. If you write 2 multiplied by 10 to the 4, that's to one significant figure. That wouldn't give you full marks. So if you see two significant figures here, make sure you write your value, your answer to two significant figures. Just before we talk about simple interest and compound interest, I want you to think about this word. So the word multiplier. So which multiplier increases a number by 3.5%? You don't need to write this in your book, but just have a think about what the answer to that question would be. So if you want to increase a number by 3.5%, you would have to multiply the value, the original value, by this, because here you're multiplying it by the original amount and you're adding on 3.5%. So moving on to simple interest. Simple interest is where we increase the original value by the same percentage over and over. So the example here is that a bank account containing £100 gets 3% interest, simple interest, each year. So you need to work out 3% of 100, which is of course £3. And what that means is every single year, £3 will be added to your total amount. So after 1 year, you would have £103. After 2 years, you would have £106. The next year, it would be 109. Then you'd have 112, 115. Just each year, you would add on 3% of 100. So using this logic, please try to answer the question on the screen. So the question at the bottom, Alex invests £2,000. Try to answer that question. Okay, so Alex invests £2,000 at 3% simple interest. How much interest will she earn in 3 years? So 3% of 2,000 is 100 multiplied by 2,000. So each year the amount of interest is £60. How much interest will she earn in 3 years? Now this question, it just asks for the interest. It doesn't ask for her total amount. So in terms of how much interest she will earn in 3 years, you just have to do 60 multiplied by 3, which gives you £180 of interest. What will her investment be worth after 5 years? Okay, now we want to think about the total amount. So we start off with £2,000 and you are adding 60, and we could write plus 60 plus 60 plus 60 until we have 5 60s, but of course it's much quicker to just write multiplied by 5. So this would be 2,000 plus 300. So after 5 years, her investment will be worth 2,300. Now for compound interest, we're going to look at a similar example where we start with £100, we get 3% interest. However, the 3% is compound interest, not simple interest. So with compound interest, you work out 3% of the initial amount. That gives you 103 at the end of year 1. At the end of year 2, instead of doing 3% of the initial as you would for simple interest, you work out 3% of the amount you have at the end of year 1. That would give you 106.09. Then for year 3, you work out 3% of 106.09, and you'd add it to 106.09, and that would give you the value which you have at the end of year 3, and you'd continue this process. You'd go on and on. So let's think about the differences. To answer this question, how much will be in the account after 4 years? Well, for compound interest, you'd have to do the initial amount multiplied by 1.03. This would give you the amount after 1 year. Then multiplied by 1.03, this total would give you the amount which is in your account after 2 years, multiplied by 0.3 again, which would give you your amount, the value which is in your account after 3 years. And if you multiply by 0.3 again, well, that would give you your total, the total money you have in your account after 4 years. So of course the shorter way of doing this is writing 100 multiplied by 1.03 to the power of the number of years you want to work out how much money is in your account after. So of course that's reflected in this. So this is the general formula: the original amount multiplied by 1 plus or minus the percentage over 100. So in the previous question it was 1.03 because it was 1 plus 3 because it was 3% over 100. And of course the percentage would vary question by question. N, of course, is the number of periods. Usually, for the bank account example, it would be number of periods going up in years. But of course, it could be the units could be different. It could be days, hours, minutes, or any other measures of time. The plus or minus is important because with compound, of course, compound interest is a compound growth example, but you have compound decay examples. Like, for example, if you were to buy a car, the value would depreciate, and so you would get a lot of questions where they give you the value of a car and they want you to work out how much it is worth after 5 years, for example. And in that case, you would have to do 1 take away the percentage over 100. And we will look at some examples like that as well later on in today's lesson. Please make a note of this formula, and I think it's really important to understand it. If you understand it, then it would become second nature to you when it comes to using it. But don't just try to remember it without actually understanding what is going on here. I'm going to go through 3 examples. So a compound growth example, a compound decay example, and another example where we're going to work out the value of n using some information which they will give us in the question. So we'll start off here in a question where it says James deposits this amount into a savings account. So already think about the clues in the question. If this person is putting his money into a savings account, he's going to want his savings to grow, right? And so, I mean, it says it up here, but from reading the question, you know that this is a compound growth question. It's not compound decay. So the compound interest rate is 4%. Calculate how much money he will have after 6 years. So I'll write the original amount multiplied by 1 plus 4 over 100 to the power of 6, because we want to know how much money he has after 6 years. So if you were to type that into a calculator, you would get this as your answer. Example 2, exactly the type of example I talked about, where someone buys a car for this amount. The value of this car will experience compound decay at a rate of 25% per year. So they've given us the units for the time as well, the time period. Work out the value of the car after 8 years. So original amount multiplied by 1. Here we're going to write take away because it's compound decay. 25 over 100, of course, to the power of 8, because we want to know the value of a car after 8 years. So here it is. Example 3. So it's slightly different. Now, a train ticket from Leeds to Liverpool costs £50. The ticket increases in price at a rate of 10% per year. How many years will it take for the train ticket to have a future cost of £80? So I'm going to write what we have, 50 multiplied by 1 plus 10 over 100 to the power of n, because that's what we want to work out, equals the price which it will be over time. So the future cost, right? And so we want to know what n value would give us, would I guess help us get the cost from 50 to 80. Well, what you have to do here is substitute different n values and see what your so substitute n values into here and then see what different results you get. So when you substitute n equals 2, your right hand side is 60.5. So of course that means we're going to have to substitute a higher n value to get to that 80, because remember our target is this 80, right? At the moment we have 60.5. N equals 4 gives you this. Again, we have to go higher. N equals 6. Okay, now we've gone too high. We're at 88. If you substitute n equals 5, then you get 80.5. So we've just we've just overtaken that cost of £80. And so as you can see at the bottom of your screen, n equals 5 gives the closest answer to £80. So it takes approximately 5 years for the train ticket to increase from £50 to £80. Of course, if you want to do further practice, then feel free to click on this link. I'm not sure what I drew on it, but yeah, click on this link and you will look at similar examples. I guess you could look at similar examples to this one if you're still stuck. Now that we have identified our dependent and independent variables, how do you guys think that these two will look like on a graph? So this is how they would look like. Let's say PR over 100 is a constant, so I'll call it K. You have K multiplied by N. K multiplied by N just gives us a linear line, a linear graph. So as you can see, the simple interest graph is just a straight line. So Kn, you could write Kx, y equals Kx is an example of a linear graph. The compound interest one is a bit more interesting because this n is clearly an exponent. And so here we have if we say this is our k, then it's k to the n. And so that's why the compound interest curve looks like a exponential curve. So k to the power of x. Now, of course, this is just for compound interest. How do you think the graph for compound decay example would look like? Well, here it is. Exponential growth, so compound interest, for example, is denoted by a graph which is in this form, so k to the x. And exponential decay, well, the graph looks like this, where it's starting at a very high amount and then it continues to decrease until it plateaus and starts to level out at the end, as you can see here. The equation could be in form y equals k to the negative x. Now, this is something we will look at more next lesson, where we talk about transforming curves and transforming lines. There are so many real-life examples in which exponential growth occurs. One of the most relevant ones today is, of course, the spread of coronavirus. So on average, one person will pass coronavirus to 3 others. What happens if that continues for 10 passes? Demonstrate this on a graph. So have a go at answering this question. I'm now going to click on this link. We're going to watch the video to find out the answer to this question. So what happens if this spreads for 10 passes? So I'll just pause it here. So this is a tweet from the West Bromwich Albion Football Club account. It says, "Don't pass it on. On average, one person will pass coronavirus to 3 others. Here's what will happen if that continues for 10 passes. Hashtag stay at home, save lives." So they've done this tweet to highlight the importance of staying at home. So one person has coronavirus, then they've passed it on to 3 people. Now, 3 people have coronavirus. Remember, each person passes it on to 3 people. So 3 multiplied by 3 gives you 9. Then if we play it on, 9 multiplied by 3 is 27. 27 multiplied by 3 gives you 81. Multiplied by 3 again. And for each pass, we are multiplying by 3. So we get another pass multiplied by 3. The final pass, the 10th pass, will give us a value of 59,049. So think about that, and I mean, it highlights the severity of this situation we're in, whereby 10 passes will lead to over 59,000 coronavirus cases. So please stay at home. Please make sure you're following all the guidelines. If I were to demonstrate this on a graph, well, it would just be a graph of y equals 3 to the x. So at x equals 0, so when we have 0 passes, before the first pass has been made, we have 1 person with coronavirus. So then the first pass is made, then we have 3 people, then we have 9, and so on and so forth, and it would look something like this. So an exponential curve, I'll write here x, y, let's label it properly, number of passes and here we'll write number of COVID cases. So again, looking at exponential growth, I would like you guys to sketch these 4 on one set of axes, just so we can see how these curves will look in comparison with one another, and then answer the questions on the screen. So write down the coordinates of the y-intercept of each graph. What's the same, what is different? Write down the coordinates of y-intercept of y equals 10 to the x, and how is the graph y equals 1 to the x different to these graphs. Give yourself around 5 minutes or so to answer these questions, and then when you're ready to see the answers, then press play again on this video. So I googled 2 to the x, 3 to the x, 4 to the x, 5 to the x, and I got this graph, which is really useful because on one set of axes we can see the graph of all 4 of these equations. And as you can see, this green one here is the largest for positive x values. So 5 to the x, when x is greater than 0, 5 to the x is greater than 4 to the x, which is greater than 3 to the x, that's greater than 2 to the x. And that makes sense, right? Because think about it logically, 5 to the 100, for example, is larger than 4 to the 100. And 4 to the 100 is larger than 3 to the 100, and so on and so forth. But let's think about why. If you look carefully here, the green line is the lowest of them all, and the blue line is the highest. So when x is less than 0, 2 to the x is larger than 3 to the x, which is larger than 4 to the x, which is larger than 5 to the x. Well, let's substitute a value in. So let's say let's keep it very simple. 2 to the negative 1 equals a half. Now let's do the same here. 5 to the negative 1 equals 1 over 5. Which is larger, 1 over 2 or 1 over 5? Of course, 1 over 2 is larger than 1 over 5. If you were to extend it and make the values even smaller, let's say 2 to the negative 3, that equals 1 over 2 cubed, which is 1 over 8. And compare it with 5 to the negative 3, it's 1 over 5 to the 3, which equals 25 times 5, so 125. Now the gap is getting larger. Look, 1 over 8 is a lot larger than 1 over 25. So I thought that was quite useful just to interpret that graph for you guys. Now let's answer these questions. Write down the coordinates of a y-intercept for each graph. The y-intercepts are all the same because 2 to the 0 equals 3 to the 0 equals 4 to the 0 equals 5 to the 0. They all equal 1. And so the coordinates of a y-intercept is going to be, let me move this here, 0, 1 for all 4 of those equations. What's the same and what is different? Well, we discussed some of the similarities. The y-intercepts are the same. The shape of all the curves are the same. What is different? Well, some are more steep than others. And of course, what we discussed here, of course, is a key difference. When x is positive, 5 to the x would give the largest values, and when x is negative, 2 to the x is obviously the highest curve, as you can see here. Write down the coordinates of a y-intercept of y equals 10 to the x. Well, the y-intercept would of course be 0, 1 again. Well, the y-intercept will be 1, and so the coordinates would be 0, 1. Remember, anything to the power of 0 is 1, and all exponential curves in this form, where you have a constant followed by a constant to the power of x, then that will always, the y-intercept of this will always be 1. How is the graph of y equals 1 to the x different to these graphs? Well, what is 1 to the power of 1? 1. What is 1 to the power of 0? 1. What is 1 to the power of 2? 1. What is 1 to the power of 3? 1. So this graph will look like this. It will just go through 1. Regardless of the x value, it would just go through 1 all the time. So this is a graph y equals 1. And so as you can see, the shape is completely different to these exponential curves we have on the screen. So now coming back to our starter question. In 2016, the population of the UK was 6.5 multiplied by 10 to the power of 7. Laura wants to calculate an estimate for the population of the UK in 2020. She assumes that the population increases by 0.6% each year. Using Laura's assumption, calculate an estimate for the population of the UK in 2020. So let's say 2016 is n equals 0, and we have 6.5 multiplied by 10 to the 7. N equals 1 would give us the population in 2017, or I guess, in 2017. And so that would be 6.5 times 10 to the 7 multiplied by 0.6%. But remember, it's a population growth, right? It's a population increase. So, right, 1 plus 0.6 over 100. N equals 2. Well, we just have to write 1 plus 0.6 over 100 to the power of 2. But again, that gives us the population in 2018. 2019 would correspond to n equals 3. 2020 would correspond to n equals 4. And that's the one we want to work out. So to answer this question, I'll use a different color pen. 6.5 multiplied by 10 to the 7 multiplied by 1.6 to the power of 4, because it's been 4 years, that would give us an estimate for the population of the UK in 2020. Kieran also assumes that the population of the UK increases by 0.6% each year. So then he says, okay, so he's acknowledging that the population of the UK increases with a compound growth. He then says it will take over 80 years for the population to increase by 50%, because 50 divided by 0.6 equals 83.3 recurring. So I mean, firstly, this calculation is correct. However, the method is wrong. We need to explain why his method is wrong. So what he's done here is he's saying the percentage, so let's call it R because they used R on the slide on the formula a few slides ago. So R is 0.6. R multiplied by the number of years, Rn, equals 50, right? But that's not how you work it out. Remember, compound growth involves exponents, so it has to be R to the n, right? So the reason why his method is wrong is because the population increase, population is increasing with compound growth, something along those lines. As long as you mention compound growth, if you mention that the population is increasing exponentially as well, I mean, you don't need to mention both, but I'm just saying these things would give you the mark on that question. Increasing exponentially, that's fine. Or if you just acknowledge that his method, where should I write this? All right, here. His method, Kieran's method, is simple interest. It's a simple interest example. His method any of these would give you the marks. Assuming that the population of the UK increases by 0.6% each year, show that the population of the UK each year forms a geometric progression. Now, to answer this question, you need to understand what geometric progression actually means. So I'll underline it right now. And on the next slide, you can see some notes on geometric progressions. Now, here we have a few sequences. Now, there are two types of sequences: arithmetic sequences and geometric sequences. Arithmetic sequences show an arithmetic progression, and geometric sequences show a geometric progression. So arithmetic sequences are sequences such as this one, whereby there is a common difference, the common difference in this case being 3. That means the difference between each term to the next is 3. Now, a geometric sequence, instead of of adding a value of 3, for example, you're multiplying by a term each time, and so there's a common ratio between one term and the previous term. So the second term is 3, 3 divided by 1 is 3, and then 3 multiplied by 3 is 9, and so this is actually an example of the COVID cases from the West Brom video. So you're multiplying by 3 each time. This is an example of a geometric sequence, and so a geometric progression. You don't need to write this information down in your books. I'd just like you to understand the differences between arithmetic sequences and geometric sequences. The key thing being, with geometric sequences, you're multiplying by a common ratio, and for arithmetic sequences, you're adding a common difference each time. So coming back to our previous example here, actually I'll leave the mark scheme answers here so you can see, to prove that the population of the UK each year forms a geometric progression, we need to prove that there's a common ratio, and of course we know that the common ratio is 1 plus 0.06%, and of course the second mark would be awarded for saying that the terms are generated by multiplying the previous term by the common ratio. So this second mark highlights, I guess, shows that you understand what a geometric progression is. So saying that terms are generated by multiplying the previous term by the common ratio. Your independent task is to answer at least 3 questions from this worksheet. Please try to do the final few questions. These are difficult exam questions which a lot of us struggle, so it's really important to get as much practice on these questions as we can. Remember to mark your work. A lot of you are sometimes forgetting to mark your work, so please make sure you mark your work as well. And also, if you're stuck, please make sure you're asking me for questions. Don't just leave it and pretend like this lesson hasn't happened. Please could you all scan or take a picture of your work and submit it. You know how to do that by now, so please make sure all of you do that. Remember, you have Sparks homework, which is due this Thursday. That's the homework on conditional probability, which was set last week. Please make sure you complete any overdue Sparks homework as well. Make sure you're asking me for help if you are stuck on any questions. And I'd like you to have a look at this graphic, which some of you have already seen. I emailed it to a few of you. And what it says is that using Sparks Maths for 4 hours per week on average helps increase our students' predicted GCSE Maths results by 1 GCSE grade. So that's straight from the Sparks website. Of course, they have a really large sample size which they're working with. So I'm sure if you guys hopefully do 4 hours per week, I know it sounds like a lot, but you will see that you're going to make a lot of progress. Please make sure you complete all your compulsory tasks as well as the optional and target tasks. Please try to complete those, because that will mean you're spending a lot of time on Sparks, and chances are it will help you significantly in your GCSE Maths results. Of course, if you have any overdue remote learning assignments, please make sure you complete those as soon as possible. Of course, I emailed some of you separately, so check your emails, check your Hampstead School emails to ensure you're not behind any of your tasks. And last thing I've written here is recap. We do learn a lot of topics, but there's no point if you don't flip through your notes. I'm just thinking the last few months we've done some really difficult questions related to trigonometry, equations of tangents, and circles, completing the square, turning points. We've done so many difficult questions, which is great, but I do worry that if you don't recap and flick through your book, you will forget how to answer some of these questions. So please make sure you're recapping that work as well. Please, of course, make sure you're getting a lot of practice done, a lot of independent learning at home. And of course, if you have any questions, if there are some difficult exam questions which you can't answer by yourself, feel free to contact me. I will try my best to help you as well. So yeah, that is it for today's lesson. Please make sure you submit your tasks, and I will speak to you guys next on Thursday. Take care, stay safe, save lives.